Previous lesson, we talked about how to evaluate limits algebraically. Today we're going to do more of, um, of evaluating limits, but it's just these problems are going to be a little bit more step and time intensive, so a little bit more involved than what we were doing with factoring yesterday. But the idea remains the same, where we're trying to, after we evaluate the argument, we're going to come across 0 over 0, which indicates that there's a hole, and doesn't mean that the limit doesn't exist. It just means that we have to do a little bit of work to clean the expression up so that we can identify where the hole is. We can eliminate the hole, reevaluate, and get to where the limit is on the graph. Very much like the previous lesson, where we're just focusing on this third step, this simplifying. It's just that today there are different variations of problems that we have to explore. Okay. So the first is these types of problems that involve conjugate method. So here's the steps here. If there's a sum or difference of two terms in the numerator, then multiply the numerator and denominator by the conjugate term. So we used conjugate in the past to rationalize the denominator. So in the past, maybe you had a problem where you had to find a way to get the radical to go away, and the way you do that is you multiply the numerator and denominator by the conjugate, and the conjugate term is just going to be the same terms. We just change the signs. So, and then whatever we decide is the conjugate, where the conjugate term, we also duplicate that above. Okay, and then the idea is that if we were to FOIL this out, the radical term will disappear and will be rewritten in a different form. Okay. But for us, for this type of problem, we're not going to be rationalizing in the hopes of getting the denominator to clean up. The point of conjugate terms for us, for this scenario, is to find a way to get our numerator and denominator to show us a common term that we can eliminate and find the hole. Okay, so if you look at example 1, these are the problems that most likely are going to be involving this conjugate method whenever you see a radical as a portion of the numerator. But first things first is we're always going to be evaluating our argument. Okay, so we're going to plug in the 4, and let's just see where we are before we jump too far into our steps. Okay. So first thing we do is we plug in the 4. So we get 6 minus radical 4 plus 32 all over 4 minus 4. I'm just replacing the x's with 4's. And let's see what we get in return. So we get 4 plus 32, that's 36. Root 36 is going to be 6. And so 6 minus 6 is 0. So we get 0 over 0. Again, I'm using the arrow to, just for future reference, equal sign tends to be, especially midway through problems, tend to be a situation that College Board may take off points for. So I think the safer thing is just to use arrows if you're progressing from one step to the next in your problem. So if we get 0 over 0, we know that the limit does exist, but we're kind of at a halfway point where we have to do a little bit of work. And we want to be able to clean this numerator up so that we can get that, hopefully get a version of the x minus 4 to come out, so that we can cancel, eliminate, and so that we can reduce and simplify, just like how we did with the previous factor rational expressions. So the way that we're going to proceed is we're going to find the conjugate of the numerator. So this seems kind of strange, right? Usually we're finding the conjugate of the denominator, but in this case, it's not the denominator that needs to clean up. It's the numerator that we're trying to get this into a form that is more useful, more helpful for us. So I'm going to find the conjugate term for the numerator. So the conjugate term is going to be the exact same copies, exact same as what I see here. The only thing I'm changing is this minus sign, okay? And don't change what's inside the radical, okay? So these terms are kind of set. The only thing we're going to change is that middle. Okay? So I'm going to multiply by 6 plus root x plus 32. Now we're going to be expanding this out. So a couple of things I want to bring to your attention is that this looks messy, okay? But this numerator is going to clean up very nicely. Whenever you're multiplied by the conjugate term, the point of conjugate terms is that it allows for radicals to disappear. It allows for the expression to clean up nicely. So when we expand this out, we only have to worry about multiplying the first pair and the last pair. You don't have to worry about multiplying and adding the middle, because the middle terms will just wash out. They'll kind of cancel each other out. So I'm just going to be multiplying the 6 and the 6 together, and I'll multiply the two radicals together. Okay. All right, so I'm going to take my step to clean up the numerator. So we have 6 times 6. This gives us 36. We're going to ignore the middle terms. Technically, this is minus 6 root x plus 32, and then plus 6 root x plus 32. And we know that those two will just kind of wash out. They're cancel out. So we're going to ignore them. Just going to focus on the last pair. So if I multiply two radicals together, I'm just left with what's inside the radical with the radical removed. So I'm just left with x plus 32. But here, something we got to be aware of is that there's a negative times positive, which is a minus. But there's going to be a parentheses that we're going to have to deal with a little bit later. Okay, so we don't want to forget that this minus is going to affect everything that comes after or what's inside the radical. So we're going to have to clean that up a little bit later. All right, so there's the numerator. The denominator, here's the thing, the denominator we're not going to expand out. Okay? And the reason why is because this is what we're trying to target. You see this x minus 4, and then limit as x approaches 4. This x minus 4 is what is causing the denominator to go to 0. And we're hoping that the numerator will produce some form of x minus 4 so that we can cancel out. That's the whole purpose of this, this process, is we're hoping that some form of x minus 4 will cancel out so that we can eliminate and cancel out. So we don't want to try to expand this out. If we expand this out, then we get, this x minus 4 is going to get lost, and we're not going to be able to have it, we'll have a harder time eliminating. So we're going to leave the denominator alone, because the denominator is already separated in a way that, in the form that is going to be, is where we want it to be. Okay, we want that x minus 4 there. All right, so now I'm just going to clean up the numerator. I'm going to distribute the negative through. Okay, so we're just going to resolve the, this numerator here. So we get 36 minus x. I'm just going to put this over here. The result of this is going to be 36 minus x minus 32. I'm distributing the negative through. So now that gets me 4 minus x. So the numerator cleans up nicely. things are kind of beginning to take shape in terms of matching up for us. Okay, so now we see the 4 minus x, we see the x minus 4. We know we're moving in the right direction. These are, the numerator is becoming a lot more, it's matching a lot better than it was before, right? But it's still not a perfect match. The 4 minus x, the x minus 4, they're off by a factor of -1. So I'm gonna just factor a -1 out. Okay, I'm gonna maintain balance here. So if I factor a -1 out, I have to change the signs of both these terms. So if I factor -1 out, the 4 becomes negative, the negative x becomes a positive x. So I'm going to put the x in front just to make it easier visually to match with the denominator. And now we see that we have a perfect match, right? And this is why we did not want to expand the denominator, right? If we expand the denominator, it becomes a whole mess, and we're unable, we have a harder time trying to figure out what we can cancel out. But the x minus 4 is already there for us to make that next step. So we want to kind of avoid the temptation to try to expand this out. So we're just going to expand the numerator out. And now we see that we have a perfect match, right? Cancels out nicely. The whole has been removed. We have a cleaned up expression. We now are going to reevaluate. And we're hoping that this reevaluation will move us to a real number. And if we get a real number, then that's going to be our limit. Right? So we'll plug the 4 in for the x. So the 4, there's only one x to plug in, and that is in the denominator. All right, so 4 plus 32 is 36. We get root 36, which is 6. 6 plus 6 is 12. So we get -1 over 12. All right, the second type is this type of problem where there's a complex fraction and we need to find a common denominator. So we see that there we have a fraction within a larger fraction. So first things first, though, we don't want to do anything that is different than any other problems that we've done in the past. We just want to evaluate that argument first. So plug 0 in for x. Okay, arrow. 1/4 minus 1/4 is 0. We get 0 over 0. So we are, again, staring at a problem that has a similar result halfway through. We see that there's a hole in the graph. We know we have to resolve that hole. And the way that we're going to do it is we're going to find a common denominator within this numerator portion. All right, so I'm looking at the numerator, and I'm just going to focus my attention on this piece right here. Okay, I'm going to try to clean this up so that I won't have to deal with a fraction within a fraction. So I'm going to find a common denominator within just that portion. So the 1 over x plus 4 and the 1/4, they both, we can find a common denominator by putting those together. So my common denominator is going to be 4 and x plus 4. Now, this is my new denominator, so I have to balance, right? So the x plus 4 is missing a 4 between this fraction and this fraction. So I'm going to balance by multiplying the numerator and denominator by 4. So my new fraction has a numerator of 4, and then moving on to the second fraction, 1/4 and 4 over x plus 4. The 4 is missing the x plus 4, so I need to balance by including an x plus 4. So that means I need to balance it by multiplying by the numerator by x plus 4. So x plus 4 here. So I'm just focusing on the numerator here. Now that I have common denominators, I'm going to push these together to be one fraction. And I'm going to combine the numerators together. So 4 minus, now this minus is going to affect everything that comes after it. So it's going to be 4 minus x minus 4. So this leaves me with negative x over 4 over x plus 4. Now that is just going to be for the numerator portion here. Okay, so I have cleaned up this numerator to now look like this. I now have it under one fraction. All right, so these are equivalent. It's just that now I have it under one fraction. And now this is going to be a little bit better place for us to move forward. Now, we don't want to forget that as we clean up the numerator, this is still all over x. Do we see that? It's still all over x. We've just cleaned this portion up so that we get these two fractions to be merged into one fraction, but it's still a complex fraction. Okay. So now, is there anything that we can do to maybe collapse these terms together so that we're not dealing with a fraction over a fraction? So what I'm going to do is I'm going to move this x up to this level so I can figure out what matches, what cancels out, what I can combine. So I'm going to multiply this x denominator by 1 over x. And whatever I do to the denominator, I can also do to the numerator. And now that balances out, I can take this out. So this is now my new problem, a problem that is easier for us to move forward. Now, I'll rewrite this again. So what do we see here? We see that this cleans up nicely, right? The negative x and the x, one's in the numerator, one's in the denominator. Anything that is multiplied, numerator and denominator, that we can cancel out. There's no plus or minus that's affecting these terms that prevents us from being able to cancel out. So the negative x and x, sorry, the x cancels out, the negative is going to stay. But that is where the hole is, right? The hole was this x. And now we've created a situation, we've rewritten it in the form where we get that x to show up. And now we can clearly see what is causing that 0 over 0. We're going to eliminate the hole. And that is going to bring us to to a continuous function version so that we can actually evaluate the limit from here. So we have a cleaned up version. We're now going to evaluate. The hole has been removed, replace the x's with 0, and we get negative 1 over 4 times 0 plus 4. Okay. 0 plus 4 is just 4, so we get negative 1 over 4 times 4. And 4 times 4 is 16, so negative 1 over 16. Okay. All right, one more new topic, and this is kind of separate, is this idea of squeeze theorem. Okay, so the idea of squeeze theorem here, let me read this here. It says, in the graph below, we have a lower function and upper function that have the same limit at x equals 1. So the lower function is f of x, the top function is h of x, and I'm going to highlight the middle function. It's this g of x. Okay. So the middle function has the same limit value because it is trapped or squeezed, sandwiched between these two outer functions. Okay. So here's the definition. Here's the idea with squeeze theorem. Squeeze theorem says, if I can somehow show, well, first off, the problem has to establish for us that there is a lower, middle, and upper function. Okay, it's always, these functions will always kind of stay in in this relationship with one another. F of x is always less than or equal to the middle is always less than or equal to the upper. Okay, so once we've established this relationship, then we know that this g of x is always going to fall between f and h. And the idea is that if I can somehow show that the limit as x approaches a value for the lower and upper is the same, then g must also be that value because it's squeezed between the middle, between the outer ones. And this is useful for problems where we are either unable to find the limit or we don't have enough information to find the limit, but we do have something, two anchor points to work with. And if we can show that these anchors are behaving in a way that is that we can conclude that they are at the same value, then we can make that conclusion that the middle is also that value. So suppose that the limit as x approaches a for the lower function is a certain value, certain limit, then the middle one is also that limit. Okay, so here's an example to kind of show that. Let's say we have h, we have f, and g falls between f and h. So if I can find the limit as x approaches 0, I don't know what g is, but I do know what h and f are. So if I can find the limit of those functions, then I'm able to get the result. So I'm going to show this key here. The limit as x approaches 0 for the lower function is x squared plus 1. The limit as x approaches 0 for the upper function is h of x, which is just 1. So I'm going to do the limit work for the outer functions, for the outer pieces. And here I'm just going to evaluate it like I normally would. Plug in 0 in for x, I get 0 plus 1 was 1. Middle is unknown for now. I'm going to do the upper. The upper, if I plug 0, there's nothing for me to plug in. That's 1 is going to stay 1 as well. And now we see that these are matching. Okay, if these are the same, then the middle one must be the same as well. So by squeeze theorem, we can therefore conclude that the limit as x approaches 0 for this g of x is equal to 1. Okay. Now this squeeze theorem breaks down if we don't have this relationship established, or if these are not in agreement. Let's say this is equal to 1 and this is equal to 3, then there's still a lot of unknown. We don't know, okay, we know g is between 1 and 3, but it's not going to allow us to pinpoint a specific value. So squeeze theorem is really only going to be successful if there's a relationship established between lower, middle, and upper, and the lower and upper happen to be the same value. Then we can we're able to use just common sense to identify, okay, the middle one, if it falls under this relationship, then I can conclude that the middle is also equal to these values.